Previously, we treated the resistor, the inductor, and the capacitor all separately. What we're going to do now is put them all together. Now, I introduced something called the phase angle. And I think I misspoke. I said that the phase angle was positive for the inductor and it was negative for the capacitor. It's actually positive for the capacitor and negative for the inductor. But essentially, we're going to have to remember some of the previous ideas that we had. Resistance, which is R, is measured in ohms. It tells us for resistive load how much current we get for a particular voltage. We also calculated something called capacitive reactance, okay? This is also measured in ohms. It tells us how much current we have flowing to and from a capacitor, okay, for a given voltage applied. And then, of course, there was inductive reactance, which is also measured in ohms. Okay, so all three of these are going to be important as we go forward. And also this idea of a phase angle. How is the current oriented with respect to the voltage? None of this is easy, and we're only going through this superficially. So just try to get some of the basic ideas. Don't sweat the details too much on this, unless you're going to go on to an electrical engineering course and analog circuits course where, well, this becomes really, really important. Okay, so going forward, again, if I take an inductor, a capacitor, and a resistor and put them all in series, the inductor and the capacitor are going to have an effect on the phase of the current and the voltage. The resistor has no impact on them. But basically, there is going to be a difference between what the current is doing, okay? So a phase angle right here, and what the voltage is doing. So the peaks and valleys don't necessarily line up unless our phase angle is 0. Okay. Now, let's go forward. In any instant, the voltage across the RLC combination is due to a voltage drop across the resistor, which is just V equals IR. The voltage across the inductor, okay, which is related to the rate of change of current, as we saw. Basically, it's the back EMF, or most closely related to the back EMF. And VC, which is the charge, or proportional to the charge building up on the capacitor, okay? So what we can do here is go back to our phasor diagram and say, let's say that this represents the current right here. So we're going to do the voltage with respect to what the current is doing in time, okay? The voltage across the resistor is going to be in phase with that. So this contribution right here isn't going to affect the overall direction of our total voltage vector. We know that for the capacitor, the current leaves the voltage across the capacitor. So our capacitive voltage across the capacitor is going to be 90 degrees behind the current. Likewise, in the inductor, the current lags this voltage right here. Again, it's 90 degrees. So basically, what I'm going to do here is when I want the total vector right here, I'm going to add this vector to this vector to this vector, and that's going to give me my total voltage. All right. In this particular case, if I had VC to VL, okay, if I had VC to VL, I'll get a smaller voltage that maybe points off in this direction right here. Because as you can see, VL is a little bit greater than VC in amplitude. Then, if I add this vector now to this vector, okay, I'm going to get my new voltage vector, my total voltage vector, which goes off like that. And phi represents the angle between it and the current. Okay, yes, it's complicated. Yes, it's not a really visual thing, but at least a phasor diagram helps us a little bit in understanding this. So the instantaneous voltage across the resistor is in phase with the current. The instantaneous voltage across the inductor leads the current by 90 degrees. The instantaneous voltage across the capacitor lags the current by 90 degrees. We add them all together, okay, and we get the total voltage of the system, and we compare how that lines up with our current at the top. Fortunately, if we add these three vectors together, we can get this phase angle, okay? We can get this phase angle by using simple trigonometry, okay? V0, which represents the total voltage vector, okay, is going to be equal to the square root of VR squared plus these two differences, VL squared minus VC squared. Okay, again, I'm just adding three vectors together. We know how to do that already. All right, because VL and VC are 180 degrees different from one another, we can just take the difference between the two and get a new vector, VL minus VC. Because it's 90 degrees out of phase with VR, I then use the Pythagorean theorem to find out the resultant of the two, and that gives us this V0. Okay, now the phase between V0, which is the total voltage of the system, and VR, which is in phase with the current, okay, the angle between these two is basically equal to this expression right here, because tangent of theta is equal to the y component over the x component. In this case, this would be y, this would be x, if we're imagining this in some rotational coordinate system. All right. So if I'm calculating the phase angle for the system, all right, what I need to do is, first of all, calculate what is my inductive reactance. Okay, what is my inductive reactance? What is my capacitive reactance? If we remember earlier, inductive reactance was proportional to the frequency. So it was omega times L. The capacitive reactance was 1 over omega times C. Okay? Now, you're going to get an interesting situation. If we set XL equal to XC, okay, this is what we call the resonance condition, okay, because this will set these two to 0, which means that the angle is equal to 0. The voltage and current will be in phase. Now, let's review what we know already. We know that a resistor has a 0 degrees phase angle with respect to the voltage and the current. All right. With the capacitor is 90 degrees out of phase, where the voltage lags the current. For the inductor, the voltage leads the current by 90 degrees. Okay. We're going to calculate impedance later on, so don't worry about that so far. And if I have a purely capacitive load, it will be between 0 and 90 degrees in terms of the phase angle. If I have a purely inductive load, it'll be between 0 and 90 degrees in the positive direction. Okay. Now, we can calculate something called impedance, which puts together all the different effects that the resistor, the capacitor, and the inductor are going to have, okay? This unites resistance with inductive reactance and capacitive reactance all together, okay? This gives us something called impedance, which also has units of ohms, which will relate the maximum current that I have to the voltage and these other factors, okay? So impedance is almost like the overall number of ohms that the circuit is going to have. And it is important to realize that Z is a function of the frequency, okay? So Z is going to change as you change the frequency. But basically, think back to when we were just doing Ohm's law for DC circuits. Current was equal to voltage divided by resistance. The only thing that was affecting the current was the resistance. Now we've introduced this new concept of impedance, where we know what the capacitor is doing is going to affect the current, what the inductor is doing is going to affect the current, and what the resistor is doing is going to affect the current. By putting them all together, we get this new value Z. And again, it behaves just like we had with Ohm's law. We just say that now, instead of I equals V divided by R, I equals V divided by Z, where this represents the maximum current and the maximum voltage. Okay? So, think about this. If something has a very low impedance, then that means it'll have a lot of current for a little amount of voltage. If something has a high impedance, there will be very little current flowing for a given amount of voltage. And that's really what impedance talks about, okay? In terms of resonance, when XL equals XC, when the inductive reactance equals the inductive capacitance, our Z just becomes purely resistive, okay? Now, this is going to have consequences later on, because if you remember when the inductance, an inductor and a capacitor produced a oscillator, okay? And we said that the oscillator was in resonance when omega equals 1 over the square root of LC, right? Well, let's think about this, okay? If I set XL equal to XC, what I'm doing is saying omega L is equal to 1 over omega C, okay? Let's write this in a different way again. I'm going to multiply both sides by omega, so this omega becomes omega squared, and omega divided by omega cancels out. Now I'll divide both sides by L, okay? And this L will cancel out with this L. And I get omega squared is equal to 1 over LC, okay? Our resonance condition for the LC oscillator was 1 over the square root of LC, right? Hey, that's when your impedance is the minimum. At that frequency, your impedance goes to be completely resistance. Okay.